And we're going to stay with glucose transporters for a while. Okay, so we're going to stick with glucose because it's been sort of our poster child of things that need help to get across the membrane. And besides, it makes a great story. How many of you are in neuroscience? Okay, 1, 2, anybody else? Just 2 of you?
Oh, wait, as a major or as the class?
No, as a class, in the
Yeah.
class neuroscience. Yeah, okay, okay.
did last year.
Oh, who did? All right, good. Okay, good. Well, I'm going to mention some things that I don't know a whole lot about, so it's up to you guys to maybe fill in some gaps. Not necessarily today, but eventually. Okay. So for the rest of the week, we're going to focus on symporters and antiporters. So we're looking at transporters that use gradient energy. Okay, and as we discovered, a lot of times the source of energy is the sodium ion moving down its concentration gradient. And there are lots of sodium-driven transporters. So we're going to cover the glucose sodium symporter, but the same mechanism works for moving amino acids across the cell membrane, and for when amino acids have to be actively transported, not passively transported. And neurotransmitters. The reuptake of a lot of neurotransmitters is driven by a sodium gradient. So this is a very common way of moving things up a concentration gradient. So we're going to pick on the sodium glucose symporter. We'll start out with the one that you find in the intestines, okay, on the apical membrane. Okay, of intestinal cells, and then we'll take a look a little bit at how it does active transport. And we'll talk a little bit about the kidney, because we're going to find a similar protein in the kidney. So I'm going to start drawing. I like the books. If you look at figure 11, who's 11? No, figure 11:9. They show a real nice model of a sodium glucose symporter, and I kind of like the model. I'm going to draw my model. Talk about how it differs from so that we're going to show you outside and inside the cell. Okay, let's imagine being in the intestine. This is an intestinal cell, and so what is outside the cell is actually the lumen of the intestines. Okay, you just ate a meal. Could have been carbohydrate rich. You got a lot of glucose that you have to absorb and deliver to the bloodstream. Okay, so the first process of absorbing is getting it out of the lumen into the intestinal cell. Okay, so in the process, we're going to, essentially what we're doing is we're going to move 2 sodium into the cell, 1 glucose into the cell. Okay, sodium's moving down its concentration gradient. Glucose is moving up a concentration gradient. Okay, so where are we going to find more glucose? In the lumen or in the cell? In the cell. This makes no sense to me. After eating like oh, my favorite food, Butterfinger Blizzard, this makes no sense to me at all, but this happens to be the case. So high concentration of these. Okay. Relative to the already high concentration of glucose in your intestines after a Butterfinger Blizzard. Okay, these symporters, I think all of them use cooperativity. Cooperative binding. And because they use cooperative binding, we can't discuss or describe KMs anymore. So there's no KM discussion on this because we're doing cooperative binding. So the binding of one ligand I'm going to have to erase this. Increases the affinity for another ligand. So when these carriers are empty, there's no ligand bound, the carriers have fairly low affinity binding sites. So low affinity binding site for sodium and low affinity binding site for glucose. Okay? When a sodium ion binds to the transporter, then the affinity for the carrier for glucose increases a lot, as well as the affinity for sodium increases a lot. So the sodium concentration outside the cell is about 145 millimolar. It might change from one circumstance to another. Yep. On the inside of the cell, it's about 12 millimolar. On which side of the membrane is sodium more likely to bind to the transporter, even under low, even when the transporter has a low affinity? On the outside, okay? So glucose plus the sodium at 145 millimoles is going to favor the formation of a carrier, a sodium glucose carrier complex. Okay? So a lot of reactant is going to push this reaction forward in favor of the formation of okay, so my circles are the sodiums. Okay, and glucose lines. And notice I made the dent deeper because we now have an increased affinity for sodium and an increased affinity for glucose. Okay. So the high concentration of sodium outside the cell pushes the formation of this particular complex. Once the glucose and the sodium bind, okay, this is a tricky part. there's a conformational shift where the members, where the three ligands, the two sodium and the one glucose, are really not on the inside of the cell or the outside of the cell. They're sort of in the interior of the protein. So this would be a closed state. And here's another one. Here's another open state. Okay? And it turns out, and this is kind of frustrating, that it turns out that once this closed state is achieved, it can go this way, or it can go this way. And it's just stochastic which way it goes. So what if it bounces back to this state? What's going to happen? Nothing. Okay? The high concentration of sodium keeps the sodium on and the glucose on. But what happens if it flips into this state? Yeah, with this, inside the cell, if there's only 12 millimolar sodium, okay, that's going to favor the reverse reaction, okay, the dissociation of the sodium. So the two sodiums come off, and if they come off, then the glucose comes off. Okay, so this whole process is really driven by the sodium concentration gradient, where we see the formation of the glucose sodium carrier on the outside of the cell, and we favor the dissociation of the sodium glucose carrier complex inside the cell. Okay, that makes sense? And it's somewhat hard to imagine that, you know, I think some of you know this to be true, that concentrations do alter the equilibrium constant and do alter the thermodynamics. So on the inside of this cell, we don't have much sodium, so we're going to dissociate the sodium. Dissociate the sodium, we lose the affinity for glucose, so everything kind of comes apart. Then we can go back to then we create another closed state. Okay, and I made it kind of little to emphasize that there really aren't high affinity binding sites. Things get weird, yeah. Usually my fingers grow. Okay, and here's another closed state, which can go this way or it can go this way. I don't think there's any sequence that it's shooting for. But if it goes to this direction, what's going to happen? Nothing. It's not going to reload because the sodium concentration is too low. Okay? And what's going to happen if it goes this way? We reload and start the whole process over. Okay? So this is indeed a concentration gradient driven process. It's just so hard to intuitively also think, yeah, energy is released in the process. There is a negative delta G in this whole process. Okay, any questions about this? And I'm going to give you some other examples besides glucose. Yeah.
What if, like, after it closes for the second time, it opens up again inside the cell and,
Mhm.
like, sodium does bind? What happens?
Then what do you think would happen? Then glucose would bind.
But is there enough, like, energy in the concentration gradient for it to go back up again?
Yes. There's a steep concentration gradient with sodium, a steep enough one so that the exit never happens. Okay, it's amazing how steep a glucose concentration gradient you can maintain. So what's going to happen if this thing runs about 10,000, 100,000 times? What's going to happen to the sodium concentration inside the cell? It builds up. So what are we going to do?
Get rid of it.
Yeah, any clues as to what the protein is that's going to get rid of that sodium? It's the most common plasma membrane protein in your body.
The sodium potassium.
Yeah, the sodium potassium pump, which we will get. Okay. All right, let me see if there's anything else. Oh, so since I'm asked this question, starting on tomorrow and then on Friday, we're going to start calculating the amount of energy stored in this concentration gradient. Okay, so 145 millimolar sodium out and 12 millimolar in. How much energy is stored in that gradient? And one of the things we're going to discover is that that gradient will support a glucose concentration gradient of 3,000-fold, meaning that there could be 3,000 times more glucose inside this cell than outside this cell. Do you think that's even physiological possible to have a glucose concentration gradient that steep? I don't think so. I cannot imagine what the cell would be like if it had 3,000 times more glucose in the cell than outside the cell. It would be like syrup. It probably already is like the cell's already like syrup. Okay? So there's so much energy in that gradient that you're not going to run the pump backwards. Okay? But tomorrow we're going to calculate the amount of energy in that concentration gradient. Okay, I've got about 7 minutes. Oh, let me give you some other proteins. There are other things. So all of the amino acids that you ate, okay? So, I noticed that Iowans tend to love meat and milk, and so you guys eat a lot of protein, okay? And it has to be absorbed by active transport. So sodium-driven. Oh, I have another question, active transport. So I'll save this slide till tomorrow. In the brain, well, since I'm on the intestines, so glucose is taken up by active transport, okay, by the sodium glucose symporter. So when you eat, about 10% of the calories that you eat are used for absorption and digestion. Okay? So if you eat a 2,000 calorie diet, about 200 of the calories that you ate are required for getting those nutrients into your bloodstream. So the hydrophilic monomers, the galactose, the fructose, the glucose, all the amino acids, the water-soluble vitamins are all picked up in an energy-requiring way. Okay. What about fatty acids? What about the fats in your diet? They just go through the membrane. Take a lot of energy to digest and absorb. So, okay. Sodium-driven neurotransmitter pumps. Serotonin is taken back up by neurons through using sodium as an energy source. Okay, so serotonin reuptake inhibitors block this particular sodium serotonin transporter. I think it is a symporter. Yeah, it is a symporter. So the serotonin reuptake transporter is a sodium serotonin symporter. Okay, and it is a target of the serotonin reuptake inhibitors. Dopamine is also, we're gonna talk a bit about, no, it's GABA we're gonna talk about. The dopamine is also brought back into the neuron with the help of sodium. Okay, and there are certain drugs that are dopamine reuptake inhibitors that make you feel pretty good. And GABA. Gamma aminobutyric acid is also a neurotransmitter, and it gets taken up using the energy of the sodium gradient, and it also takes, that transporter also takes up chloride. And we'll talk about the GABA receptor later, probably next week sometime, just because we're going to do some sample problems. It by itself is not that important. Okay. So here's my question to the people in the neurosciences. Is for you, find out if there's other sodium-powered reuptake transporters. Also, maybe you can find some drugs that alter the serotonin receptors, the dopamine up transporters, or the GABA transporters. What kind of drugs? Okay, alter the activity of these transporters, so that generally there's more GABA in the synapse, or more dopamine in the synapse. Okay. So tomorrow we're going to look at the distribution of these sodium glucose symporters in the kidney. Okay. And I would do that now, but there probably is not. Any questions? Yeah.
So are the dopamine and the GABA neurotransmitter pumps also symporters?
Yeah, they're also symporters. Because sodium is moving down its concentration gradient into the cell, and since these are reuptake, so is the neurotransmitter moving into the cell. Okay, so tomorrow we'll take a look at the kidney. And then my favorite, we'll take a look at some math. Come here, math, COVID. Yeah. Well,
No, you said math.
I said we're doing math tomorrow.
Yes.
So bring your calculators. Have you been doing math in the neuroscience course a little bit, the equations?
Yeah.
Yeah, we're going to do a lot of